We will now consider line integrals of vector fields. So let r of t equal to the vector x of t, y of t be the position of an object moving along the curve C. So in this example, we have the curve C, and that is parameterized by r of t equal to x of t, y of t. So here we can think of this point as being r of a equal to, say, x of a, y of a. And this point here we can think of as being r of b equal to x of b, y of b. And then if we pick some arbitrary point, that point would be r of t, which is x of t, y of t. And what we would like to calculate is the work done by a force, F, on that object over a small piece of the curve, which we will call delta r. So we can imagine that we could break this curve up into small pieces. And the displacement over one of these small pieces of the curve we will call delta r. And we would like to find the work done by this force on the object over that small piece. Well, you will recall that we defined work previously, and if the force is constant, then a little bit of work is the force dot the distance traveled, in this case, delta r. So as long as the force is constant on that small segment delta r, then the work can be defined as just F dot delta r. Now if we want to find the total work done by that force on that object, we would want to sum over these delta w's. We would want to sum F dot delta r. And so that leads us to the definition of a line integral over a vector field. So we're going to let r of t be x of t, y of t. T is going to be between a and b, and that's the parameterization of a curve C. And then the line integral of that force along the curve C is going to be defined by a sum, and we're going to want to sum over all of the work. So sum from k equals 1 to n of f of r of tk dot delta r sub k. So we want to sum all of the work done over each one of these segments, delta r sub k, and that will give us an approximation of the total work done by that force along as the object moves along that curve. But we'd like to find the exact work done, and so we're going to make these delta r's smaller and smaller. So we're going to take a limit as n goes to infinity. That's the same thing as letting delta t go to 0 of this Riemann sum, so that the delta r's become smaller and smaller, and our approximations delta W become more and more exact. And then we've found the total work performed by this integral. So essentially, we can define work equal to the integral of f dot dr. And these line integrals over a force are used a lot in different contexts in physics, but work is the most natural one for me to introduce in this video. So once you define this work integral, okay, this integral of the force dot dr, the question then becomes, how are you going to evaluate this type of line integral? Well, in order to evaluate the line integral, you do need the parameterization r of t. And so you'll want to integrate from a to b, so that's t going from a to b. And we're going to do f of r of t dot r prime of t dt. So here we're thinking about dr as being r prime of t dt. One way you can think about that is that our delta r we can think of as being delta r delta t times delta t. And then as delta t goes to 0, then dr is r prime of t, which is this piece, dt. So as delta t goes to 0, dr equals r prime of t dt. And so we can evaluate this type of line integral by evaluating the force along the curve r of t, and then computing that dot product with r prime of t, and then integrating a single variable function dt. Now, the book has several notations that it uses for this line integral. And these correspond to several different notations that are used in different contexts in mathematics and physics. So for the first one, I want to recall that t is the tangent vector, the unit tangent vector that we defined by r prime of t over the magnitude of r prime of t. So let's take our line integral, and we're going to integrate from a to b f of r of t dot r prime of t dt. And then what I'm going to do is something that we've done in the past, is I'm going to multiply and divide by the magnitude of r prime of t. So I have not changed the quantity inside the integral. I've just multiplied and divided by the same value. Okay, well, if I do that, then what I get is, again, f right here, but dotted with the tangent vector. And then what we have here with the magnitude of r prime of t dt, that is what we defined in the previous video as being ds. And so sometimes the book will write this as the integral over the curve of f dot t, the tangent vector, ds. In many cases, the book will define our vector field f as the two component functions p of xy, q of xy. And so we'll have the integral from a to b of f of r of t. So p of x of t, y of t. And then q of x of t, y of t. Dotted with r prime. And r prime is going to be x prime of t, or dx dt, and y prime of t, or dy dt. dt. So now what I will do is I will do the dot product. So we're going to get p of x of t, y of t, times dx dt, plus q of x of t, y of t, times dy dt, and then all of that integrated dt. And so the book introduces this interesting shorthand for this. And that they think about it as the integral over the curve C. And then what they do is they multiply in dt. So they take this dt and they multiply it in here. And so the shorthand that they tend to use is p dx. So in some sense, they're canceling the dt. It's not something you can actually do, but they're using it just for the notation. And then plus q dy. And so many times you will see in the book that they ask you to find this integral over the curve of p dx q dy. But when you compute that integral, you should think about evaluating it in this way. So this is how you evaluate the integral, is that you need to substitute in x of t and y of t into p and q, and then dx and dy need to be computed as dx dt and dy dt. Finally, I'll bring to your attention that there are several contexts in which it's important to perform one of these line integrals over a curve that makes a closed loop. So we say that a curve C is closed if it begins and ends at the same point. And in that case, instead of writing just the integral of f dot dr, we will write this integral with a closed circle, indicating that that curve is closed. It begins and ends at the same point. So as you're working through problems on line integrals, be aware of the different types of notation that might be used. It is more likely that you will see this notation, or this notation, or this notation.